Awesome. Well, thank you for having me. I'm really excited because this is the first time I am giving a talk to European colleagues. So I can finally show a map of Spain and actually tell people about where I'm from, and they will know that it's not just Spain, but there are more places in Spain than Madrid. So I'm particularly excited about that. Kind of regret that that is on record now, but that's okay. Okay, so today I'm talking to you from where this blue dot here in southern Spain is. I'm putting my pointer on top of it, which is actually North Africa. Spain has like two small territories in North Africa, and I grew up on this one. That's where I'm coming from today. But I also spent a lot of my time growing up in this chunk, in this big egg in the province of Almeria, which is where my parents and grandparents are from. And I kind of just wanted to give you a quick geotourism summary of the area before I start talking about my research, in case you want to come to Spain sometime soon. Okay, so this is one of the things that has been happening in my hometown recently, which is this black dot down here, Melilla. We've had this like ridiculous increase in earthquake rate in the Alboran Sea over the past year. My parents told me that they could feel a lot more earthquakes sometime in July last year. And then I made a plot looking at the cumulative number of events and found out that indeed they were right. There's been a lot more earthquakes in the area since about July last year. I don't know why this is, but if anyone studies earthquake swarms or sequences, I'd love to learn more about it. And since I've been home, we felt like about an earthquake per day. It's kind of fun. Okay, and this is the other zone I told you about where the rest of my family is from, which is Almeria. And Almeria has like really, really cool tectonics. It has damage zone exposures from the Carboneras Fault that like are better than most fault exposures that I've seen both here and in the US. And this is like super accessible. It's right next to a highway, so anyone can go there. And then most recently, I went to this huge geode. It's the largest geode in Europe. I was there a couple of days ago. That's me sitting at the gate. And if you go into it and take a look to the left, what you see is this view here from the stock picture. This is in a mine. You pay 30 euros and you get a 2-hour tour, and then you get to go inside the geode and take a look at this, which was like the coolest thing I've done this winter break. Okay, and now moving on, I'm going to start talking about my research finally. Today, I'm going to be sharing with you some of the work my collaborators and I have done over the past year or so, looking at the distribution of surface deformation from the Ridgecrest earthquakes to learn something about the distribution of inelasticity, as well as the properties of the damage zone from the two earthquakes. I have like I think about a 30 to 35-minute talk. I'd love it if you just raise your hand and interrupt anytime you want to ask a question. I'm more interested in making this a discussion than just a formal talk. So first I will present the paper that's currently in press on this work. And then at the end, I'm going to show you some ideas I have for future work, and I'd love your input on those. Okay, so in the first place, why are we worrying about damage zones? Well, they are a key component of the earthquake energy budget, seismic hazard assessment, and they constitute a permanent sink of strain energy, modify the elastic properties of the shallow crust, threaten lifelines, amplify ground shaking during earthquakes, you name it, right? So because of this, damage zones have long been a focus of study for geologists and geophysicists alike. And one of the questions that motivates our work is how damage zones are defined differently for these subfields of geoscience. So I'm going to quickly go through these definitions before I start showing you my work. Okay, so let's start with geology. Geologically, damage zones are defined as the fractured and warped volume surrounding a fault. And within this volume, fracture density decays away from the principal slip surface until it reaches a background level. Here's an example from Mitchell and Faulkner, 2010, showing that fracture density is on the y-axis, distance from the fault is on the x, and you can see that decreasing with distance away. And that same approach has been taken with aftershocks, where damage zone is defined as the volume where seismicity decays until it reaches some regional background level. And then different functional fits have been used to describe the decay of damage in the form of fractures and aftershocks. People have used power laws, people have used exponentials. Ultimately, it's just something that decays very fast, but continues pretty far out. Okay, Seismologically, damage zones defined as a volume of decreased shear wave velocity surrounding a fault that hosts guided waves. Here's an example from the Calico Fault from a paper by Elizabeth Cochran in 2009. You can see the decrease in shear wave velocity, and then you reach some sort of background as you move away. And then geodetically, damage zones have been characterized as areas of reduced shear rigidity or for earthquakes that are directly imaged as the area where strain exceeds the elastic limit of the material. Here's an example from the Kumamoto earthquake from Chelsea Scott's paper. And these black lines delimit the area where strain exceeded the elastic limit. And there's been this persisting question in damage zone studies that motivates some of our work, and that is whether there are breaks in scaling within the damage zone, or in other words, whether there are different physics that operate near the fault versus farther out. So this is from Powers and Jordan 2010, their seminal paper on defining damage zones based on the decay of aftershock density with distance away from the fault. And they interpreted 3 zones from their decay in aftershock density with fault parallel distance. The first one is this zone of constant aftershock density until you reach some corner or break in scaling that bounds a zone where the aftershock density decays constantly. And then at some point, this decay meets the regional background seismicity, which is what's bounded by this dashed line. And these plots for them inspire this idea of an inner damage zone that contains one or several strands of fault core. So these sections of fault core relate to that area where aftershock density remains constant. And then some field geology studies have also supported this conceptual model of the damage zone, where there's a high intensity sort of constant area and then a decay outside of that. Okay, so measurements of the extent of inelastic zones are typically generated from a single data set, for example, a fracture or an aftershock distribution, and they often capture an integrated history of the formation, which spans multiple earthquakes as well as any interseismic, aseismic processes. And this is why we turn to the Ridgecrest 2019 earthquake to try to define the damage zone from an integrated approach, because the earthquake sequence provides this unprecedented view of the distribution of inelasticity. It was monitored from high resolution imaging, geodetic data, and earthquake catalogs, and it offers this opportunity to investigate the extent and physical properties of the damage zone, again, through an integrated approach. And the commonality of all of these data sets ultimately is that they allow us to see a point where a material has yielded within the volume surrounding the fault. Okay, so first I'm going to show you what prior studies on the Ridgecrest earthquake damage zone problem in general have found. So here is data from Milliner et al. 2021. And what Chris found in his study is that optical image correlation defines a 30 to 100 meter wide zone of inelastic strain that's centered on the rupture. That is a zone where strain exceeds the elastic limit of rock. And then other later studies have found also these zones of diffuse deformation that are 600 meters to 2 kilometers wide that receive contributions both from elastic and inelastic processes. These lines, the width of those lines represents the width of that zone that's receiving contributions from elasticity and inelasticity. And this is from Solène Antoine's work. Okay, more work on Ridgecrest. Well, SAR gradient maps illuminate a wide zone of secondary fault zone deformation. This is from Eric Schu's science paper that came out in 2020. And he found both discrete frictional slip and elastic deformation of secondary fault damage zones that were driven by Coulomb stress change. And notice that all of these lines represent those secondary damage zones, and they're pretty far away from like the main rupture, which is down here. Okay, and last seismological studies have shown 100 meters to 2 kilometer wide waveguide and low velocity zones that are variable along strike from the deployment of nodal arrays following the earthquake. These are B1 through B4. And there was a study later on that came out last December that I don't have on this talk that also deployed nodal arrays. Okay, so what do we bring to the table? We incorporate 3 new independent surface rupture mapping data sets. The first one is the surface rupture map of Ponti et al. 2020, which I don't have in this figure, and it was generated from field and geodetic observations. The second one is our own map. I made this map of the surface rupture, which was generated from the post-earthquake LiDAR data. That is what I'm showing you here. I'm going to change the pointer color. Okay, that's better. So this is the surface rupture of the magnitude 7.1 event, and this is the surface rupture of the magnitude 6.4 event. And this was generated from 0.5 meter resolution LiDAR data. Okay. On top of this, I have these orange rectangles that highlight areas where we mapped the rupture from even higher resolution data from aerial imagery. Some of it was collected from a plane while the LiDAR data was collected, and some of it was collected from a drone in the field. The white star here is this map that I'm showing below that has a zoomed in view to one of these zones that was mapped from high resolution drone imagery. This is in the middle of the main shock. Okay, and the last thing that we have in here is the earthquake catalog, the QTM earthquake catalog made by Zach Ross. We incorporate 2 earthquake catalogs to consider inelastic deformation at depth. Those are the SCSN catalog and the Ridgecrest QTM catalog. Okay, so I just want to quickly show you more about those high resolution data sets, the high resolution maps from aerial imagery. These maps were generated by myself and 4 SCEC interns and a UC Davis student. We worked last summer on developing these maps. They took about 3 months just for mapping sections A through E of the rupture. So we don't even have the whole thing mapped. And we've released this as a shapefile. They're published in an SRL paper and available for anyone to use. And they really reveal the complexity of the surface rupture, both localized and both distributed deformation. Here again is that example of the middle of the 6.4 rupture. And the drone imagery here was collected by Ian Pierce, and I made the map. Here is the southern terminus of the magnitude 7.1 rupture. And I just want to show you how complex these maps are. This was a video on the left that's not playing, so I'm just going to move on from that. Okay, and one last thing showcasing these maps. In black here, I have the rupture map that Pony et al. 2020 made based on geodesy and field observations. And it's pretty similar to the map I made from the LiDAR data. I'm plotted underneath in the form of fractures per meter square, where the kernel size is 10 meters. I am showing fractures from these high resolution maps. This was made by a SCEC intern called Ruth Prado. And what we see here is that this whole section between the step over delineated by these 2 faults also was widely deformed, but all of that deformation was essentially invisible to all of the other rupture maps. We needed this 5 to 20 centimeter per pixel data to be able to resolve that. And just a quick field view of what some of this crazy deformation looks like. You can see the main fault scarp here, and then you can see secondary fracturing extends all the way from it. Okay, the next data set that we generate and use here, which is using data that was originally published in Milliner et al. 2021, is the distribution of superficial strain mapped from satellite imagery cross correlation. We use the fault parallel shear strains measured from profiles oriented perpendicular to the primary rupture. These profiles are stacked over a 138 meter distance along strike. And we find that inelastic strains, which are about like anything that exceeds 10 to the minus 3, are limited to 30 to 100 meters away from the fault. You can see those highlighted here by these areas of high strain. Beyond 1 kilometer away, the strains become too small to resolve with this approach. So that's kind of the cutoff we use to look at these profiles. Okay. So we're going to start putting these data sets together to say something quantitative about inelasticity and in general the damage zone from the Ridgecrest earthquake. So to investigate the distribution of inelastic deformation, we look at it with distance away from the fault, and we quantify the decay of fracture density, aftershock density, and strain intensity for stacked profiles across the rupture. We measure the nearest distance between each damaged feature and the main fault. So we do this in 2D for the fracture and strain maps, and we do this in 3D for the aftershocks. And we fit these decays following the expression in Powers and Jordan 2010, which is shown here in the right, where the decay of any feature density with distance away from the fault is defined by a fracture density at the origin, which is V naught. So that for the aftershock data, which I'm showing here, that will be around here. And then a parameter that defines the distance between the origin and a break in scaling, D. so D here would be around here for the aftershocks. It's what bounds that plateau in aftershock density. M, which describes the sharpness of this corner, and we actually hold that constant equal to 2 following what Powers and Jordan does. What you do with M doesn't really make a change to the functional fit. Okay, and then the last thing we fit is gamma, which is the slope of the decay beyond the corner. So the slope of this line in log space would be gamma. Okay, so let's add more data to this plot. I'm going to add another data set. Here is the high resolution imagery from the drone and the aerial photos that we mapped. Note how that breaking scaling D has moved much closer to the origin, but that slope gamma is actually pretty similar to that of the aftershocks. Again, we fit this with the expression from Powers and Jordan, where the best fit line, its maximum likelihood fit, is it's solid, and then we have an interval of fits that's shown in the background. Okay, more data. So when I add the LiDAR data set that's shown in orange here, and then I also have added the field and geodetic map of Ponti et al., which is it's independent. Our group did nothing for that. And that's shown here in red. And then I've added the strain maps, which start at 12 meters away from the fault, because that's the kernel size for calculating strain, which are shown in gray here. Okay, so let's take a look at the distribution of fits. Panel B shows the maximum likelihood values of gamma, which is the slope, which range from 0 to 0.9, to 1.4, and they overlap within uncertainty, other than from the Pony data, which is a bit farther out there. And we interpret the similar slopes to indicate that fractures, aftershocks, and other processes that are captured by the strain maps are controlled by the same mechanism and stress field. Okay, let's take a look at the maximum likelihood values for D, which is the break-in scaling. It's the end of that plateau close to the origin. And I've also added here the uncertainty in the fault location at the surface and at depth to the plots shown by the orange shading in the background of panel A. So the corner position D is farthest out for the aftershocks at 50 meters, but it sits between 0 and 12 meters for the higher spatial resolution data, which is shown here. Okay, and it cannot be resolved at all for the strain data. So for the high resolution LiDAR field and imagery data sets, D is on the order of the spatial error of the main rupture trace location, which is shown by the shading. And it allows, many of the fits actually allow for D to be equal to 0. So for that corner, that break-in scaling do not exist. And then for the aftershock data, D is comparable to the 100-ish meter horizontal location uncertainty of events that were used to define the subsurface fault geometry in Andreas' pledge paper in 2020, which is the subsurface fault geometry we use to measure distances with here. Okay, we can also look at the decay of inelastic deformation with distance from the fault at depth. So what I've done here is I have binned the aftershock data by depth. And when we look at the aftershock data binned by depth and we look at D, we find that D migrates outwards consistent with the increasing location error from instrumentation at the surface. And we interpret that corner location from this as an artifact of data resolution and fault location uncertainty. It does not define the width of an inner damage zone. It is not showing something that's physically meaningful. And instead, the damage zone surrounding faults is defined by these power law decay of fracture density. It lacks a clearly defined edge or any break in scaling close to the origin. And just one more thought here is looking at the distribution of depth. That there's this long-standing view in fault damage zone studies that we find consistently in the field, which is that damage zones are wider at the surface than they are at depth. And to further support that that corner D is an artifact, if this was true, it would mean that fault damage zones widen with depth, which is inconsistent with observations. Okay, let's add a little bit more data here. So we compare distributions to constraints of the extent of inelastic deformation obtained from prior studies of the Ridgecrest earthquakes, which were the data sets I showed you before I started with my own data. These are shown by the gray and green bars in figure 2A at the bottom here. Okay, so optical image correlation defines this 30 to 100 meter wide zone of inelastic strain that's centered on the rupture. And then wider zones of diffuse deformation, 600 meters to 2 kilometers, that receive contributions from elastic and inelastic processes. And then seismological studies show these 100 meter to 2 kilometer wide trapped wave and low velocity zones. And note that the corners D captured by our data sets do not overlap with the edges or extent of the zones in inelasticity estimated in prior work. So again, we interpret that this corner location is an artifact of data resolution and fault location uncertainty. It does not define the width of an inner damage zone. Now, the variability of damage zone measurements from different techniques may reflect, at least in part, different levels of sensitivity to damage intensity from these techniques. For example, from the strain maps, you can't really get much farther out from 1 kilometer away for inelasticity. Strains get way too small, but we can measure these like long wavelength zones of strain that have mixed contributions. Okay, one of the things we're able to do from our Rupture maps is to investigate the sensitivity of the damage zone to lithology. So to do this, we filter fractures cutting through sediment and bedrock. It's obvious to note here that, as you can see from the map on the left, the earthquake overwhelmingly ruptured through sediment, so that the bedrock area we sample is very small. But nevertheless, we find that fracture density in sediment is 3 to 10 times higher than that of bedrock at a given distance from the fault. However, the decay of fracture density with distance is identical. The functional fit to this is identical. We think that the reduced fracture density in bedrock may reflect greater cohesion, whereas the similar decay exponents, so that slope gamma, supports that the mechanism responsible for the nucleation of fractures operates under the same stress conditions irrespective of the material. Okay. So one of the things we asked next is whether the damage decays are sensitive to unfold slip magnitude or variability. So here on the figure on the left, I have my high resolution fracture maps in the background, and each of those zones where we have the high res maps has been boxed and given a name. These are zones 1 through 5. And then on top of that, I have plotted fault slip. Also, there should be a 0 here at the bottom of the color bar. But I have plotted the slip measure from imagery cross correlation. This is from Chris Milliner's 2021 paper as well. And what we do here is we look at the magnitude of slip and variability. So this is the average slip and the average variance for each, and the variance for each of these boxes. And then we generate the fracture density decay for each of those sections, which is shown in panel D here. And what we find is that there is no correlation between corner, slope, and overall fracture density with slip magnitude. Instead, these decays are remarkably consistent throughout the Rupture, other than the fact that they have different intercepts. Okay, just a quick plot showing the distribution of fracture orientations for one of these sections. Or fracture orientations, I also have rows diagrams, but they didn't all fit in the plot. So instead I made the visual map, but I'm happy to show those later. But fracture orientations exhibit variability, but are most frequent at small angles from the fault, which suggests that a large portion of the cracks formed in shear, even close to the main rupture. This is consistent with what image correlation maps have shown. They show that shear dominates the formation within 100 meters from the fault. Okay. And earlier I talked a little bit about how the zone of inelastic deformation shown by prior studies didn't really overlap with the corners inner damage data, nor with the extent of discrete fractures, which went much farther away from the fault. I will remind you that the X values on those plots went out to 20 kilometers away from the fault. So we just wanted to compare our data sets in map view to see something about their differences and similarities, and especially thinking in terms of applying these data sets to hazard. So here I'm looking at fracture density versus strain intensity, where I've calculated fracture density using the same kernel size as the strain calculations. So on the right, panels A and C show the strain measurements from image differencing, and then on the right, panels B and D show fracture density. And this is for a section in the 6.4 and a section in the 7.1. These were both mapped from drone imagery. Okay, so we find that to a first order, areas of high fracture density and high strain do overlap. we can see, for example, here a hot zone of strain that sort of roughly overlaps with this hot zone of fracture density. But however, areas of high fracture density that are disconnected from the main fault, and you can see examples of those throughout here, do not quite show up in the strain maps. And that is because they don't have enough cumulative displacement to be resolved by the strain maps. So this one provides a potential explanation for why inelastic deformation is rarely mapped beyond the main Rupture when relying on cross-correlated satellite imagery, despite that fracturing extending far beyond. And these differences also highlight the value of high-resolution orthophotography in identifying individual fractures, which cannot be easily discerned using image correlation procedures. And again, I'll remind you of how the imagery could capture all of these secondary deformation in the step over that's just essentially blind to all of the other data sets, but that may be very important in terms of probabilistic displacement hazard analysis. Okay, so the next thing we do is we try to say something about the mechanical properties of the damage zone based on our fracture maps. And we do this based on the relationship between fracture density and shear rigidity. And we're able to estimate how much fracturing contributed to rigidity decrease in the volumes surrounding the Ridgecrest faults. This requires both integrating the density and length distribution of mapped fractures. And based on this analysis, we predict a decrease in shear modulus by about 40% immediately adjacent to the faults and sediment, and about 20% in bedrock. And both of these decline to under 1% at 100 meters away from the fault. These estimates are within the rigidity decrease range that was geodetically estimated as well as seismologically estimated. And even though our estimates are based on the fracture density at the surface, we want you to know that the width of reduced rigidity we predict compares really well to the width and velocity structure of trapped wave zones observed post-seismically at Ridgecrest. And these zones extend 3 to 5 kilometers down dip and remain fairly constant in width. Okay, so kind of starting to wrap up and bring some conclusions here. First thing is that fault and fracture mapping, aftershocks, and strain maps from the Ridgecrest earthquakes show these widespread damage that follows a power law decay with distance from the principal faults. The first conclusion we reach from this is the comparison of, through the comparison of our damage distribution generated from different data sets of different resolutions, is that the breaking scaling that's frequently reported in damage zone studies is likely an artifact of data resolution and fault location error. It is not a physically meaningful parameter. Our data suggests that in aggregate, damage zones manifest as a continuum of decay in deformation intensity. And this definitely warrants caution in the use of a single data set for determining the effective edge of damage zones in numerical models and probabilistic displacement hazard analysis. And then the next thing I want to point out first is that our measurements show that there is widespread inelasticity that extends pretty far out from the faults. And this suggests that there is some low intensity damage that is pervasive in the entire landscape. And this is actually consistent with measurements that integrate through, so far field measurements that average through a large crustal volume surrounding the faults that show these ubiquitous less than 2% velocity reduction. And we think this may be akin to the widespread damage that we're mapping pretty far out at the surface. And then the next thing to point out here is that this nonlinear decay of fracture density with distance away from the fault reveals both how macroscopic fracturing generates this intense near fault damage, that's the area here going out to about 100 meters away from the fault, that's typically what gets measured from seismic wave velocity reductions, but also that widespread damage is accruing regionally pretty far out, occupying a volume that extends tens of kilometers away from the faults. Damage zones are typically geodetically and seismologically detected along faults in the late stages of their interseismic period, which suggests that at least a portion of the widespread coseismic damage is irrecoverable. Something to note here is that this wide footprint of inelastic deformation may be representative of earthquakes on faults in the early stages of evolution in mature faults that has remained relatively undocumented, limited to data extent. The Ridgecrest footprint of imagery is so much larger than anything we've had before. But whether with widespread inelastic deformation also occurs with earthquakes on mature faults, say the San Andreas fault, awaits future events that have comparable data coverage to that of Ridgecrest. Okay, and the last thing I want to think about here is that these faults don't occur in isolation, especially in places such as the Eastern California shear zone. Places with a point far away from the Ridgecrest fault is maybe close to the Garlock fault or to whatever fault is next to that. So we need to think like, what do these far field damage measurements mean? Like, are we receiving contributions from many faults, and how much how much is that pervasively weakening the crust over time? And to consider that over multiple earthquake cycles will be some of our future work. Okay, so I will take any questions from you now, and I'm happy to show you a little bit more data for other events.